Hey everybody. We're going to talk about power and polynomial functions here. We've done a little bit with quadratics, and that's a pretty good example of polynomial functions. And the power functions are even easier than that. So let's take a look. Here is a list of some of the power functions that you might encounter. Notice the structure of it up there at the top. You can see there's nothing really too fancy about it. It is a constant multiplied by a power of x. So it's simple. One term, you got a power. Here are some possibilities. You could have a constant function where there's really a little x to the zero there. Remember, anything to the zeroth power is really one. So you could have some number. It could be a 4, it could be a 43, whatever. But a constant function where no matter what x you put in always gives you the same constant would be a power function because of that x to the zero possibility. X to the first, x to the second, x to the third. You've got some power of x. It could be anything there. Your reciprocal functions work because we could write those as x to the negative 1 and x to the negative 2. Of course, your root functions would work because we could rewrite that as a fractional exponent, x to the 1/2, x to the 1/3. So it's really any one term function with some power of x to it. And that's pretty straightforward. We know what most of these look like, and we've seen, this would be our constant function right here. X, I'll put a whole bunch of those powers in there. X to the first is going to be a linear function. X squared is going to be a parabola. X cubed is going to have that typical cubic pattern, something like that. And you could keep going with that, but they're going to start flipping back and forth between the parabolas and the cubic type function. So x to the fourth would be a parabola, only tighter, grow faster. X to the fifth would be more like the cubic, and go back and forth. And we'll see some more about that. You might get a wiggle here in the middle or something. But the reciprocal functions, we've looked at those. 1 over x does basically this, and 1 over x squared is going to be the same thing, except it goes up faster, and this everything with negative x gets flipped upside like that. And of course, you know about your cube functions too, or your root functions. Square root's going to look something like that, and cube root's going to be down here somewhere, and the fourth root and the fifth root, and so on. But graph some of those out on your calculator if you need to. Think about what they would look like and why they would look like that. Maybe build a table and put some numbers in, plot it, see what's happening. But it's good to know those. And those are all pretty straightforward because, again, there's only one term. With the power function, here's what I was talking about with the powers of this thing. And I want to emphasize that word up at the top where it says even and odd. And remember, we've seen that before in the context of functions. An even function was defined if you put in negative x, then you get the same thing as f of negative. Well, let me do it this way. If you put in, maybe I don't even need this. If f of negative x equals f of x. There we go. Okay. When I look over here and I put in 1, I get 1. And when I put in a negative 1, it gets squared. And I also get a positive 1. So whether you put in the positive version of x or the negative version of x, you end up with the same thing. They are equal. That's an even function. And it's going to be symmetric about that y-axis there. Odd functions, on the other hand, were a little bit different. For those, you got, I'll put if f of negative x equals the, well, put if and then negative f of X like that. So when you look over here at these, when I put in a positive one and cube it will say, then that would give me a positive one. If I put in a negative one, I don't get positive one up here. I actually get negative down there below. So it's kind of reversed across that. You remember that we also had neither functions, which didn't do this or that. So like a square root function, right? That doesn't have anything over here, so it's not even, it's not odd, it's not either. But the powers are interesting here, and you notice that x squared, x to the fourth, x to the sixth, x to the eighth, x to the 10th, all of the um, even powers are going to have some kind of behavior like this, where it's basically a parabola. It might get skinnier, might grow faster, whatever, but you're basically looking at a parabola. Again, when we get into the polynomial things, we might get a little wiggle down here in the middle, but I want you to pay attention to these ends. And can you see that this end is going up to infinity and this end is going up to infinity? When we talk about the end behavior, what's happening big picture here, both of those are climbing up, 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 up to infinity. Meanwhile, over here we have our odd functions, and they are the odd powers, x to the third, x to the fifth, x to the seventh, x to the ninth. Keep going if you want. But the end behavior is very different, right? Here, everything's climbing to positive infinity. And meanwhile, down here, everything is going to negative infinity. So that's kind of different. And you can really look at that highest power of x, or in this case with the power functions, it's the only power of x because there's only one term. But that will tell you, do I have an even function? Do I have an odd function? Do the um, two ends approach the same infinity, or do they approach the opposite ones? Even if I put a negative sign in front of the whole thing, let's say this is f of x, or pick some other name if you like, equals negative k of x to the p power, it's going to flip it upside down like that. But again, you see how the end behavior, they're both down. Whereas if I flip this one upside down, by putting a negative sign in front of the whole thing, then with an odd function there, I've got one up and one down, just like before. They're reversed, but mirrored across the x-axis there. And so that's the way of that. All right. Here's a little example from physics. You don't need to know the physics. I don't expect you to know this. We barely do this in physics class because this turns into a differential equation real quick, and we don't want to go there. But this little formula here tells you how much drag or how much air resistance or water resistance you have anytime there's some object that is moving through a fluid meaning gas or liquid, anything that will flow, then you got to push all that material out of the way. When you walk down the hall, you don't really think about it because the air is very thin. It's not very dense, right? You don't have to push that much mass of air out of your way. There's little molecules, they bounce off you, they go away. If you walk through a swimming pool or a lake or something, though, it's a lot harder to walk through, right? Because you have to push more mass away from you. And so this formula here kind of relates that. There's a number of factors here. C is called the drag coefficient. It's a number that you're going to look up on a table like that one over here at the right. And a sphere will move through a fluid in a certain way. Half sphere is a little bit different. Okay. It has a little bit lower drag coefficient, meaning it moves a little bit better. The cone, not so much. That one's worse. A cube, even worse, right? A big blocky thing. If you're driving a Hummer, you know, it's just a brick and you got to push all that air out. Basically, it's that shape right here. This is not air streamed. It's not very efficient at all. If you turn it 45 degrees, it's starting to look a little bit better, right? And it can push the air out better. Long cylinders do better than short ones, but you get down here to rounded shapes like most of the cars are today. You can see you have a very low drag coefficient there. So that number is important. A, the cross-sectional area. If you're driving a motorcycle versus a city bus, right? The city bus is so much bigger, that cross-sectional area, you got to push all that air out of the way. So that's the size of your object, the area of it. How big is it? Right here, rho, Greek letter rho, lowercase, is your air density or water density. So that's how much material do you have in a cubic meter. And finally, the velocity here. The faster you go, the more resistance you have because you have to push more air out of your way, right? But actually, it's a V squared, which is kind of interesting. It means your mama was right when she said if you'll slow down, you'll use less gas. She was absolutely right. Let's say we drive 10, okay? I'm going to get a certain amount of resistance here, and I'm not really interested in the number because we have all these other factors we'd have to think about. Well, let's say it's 40, okay? If I double my speed to 20, there's a factor of 2 in there that gets squared. It goes up by a factor of 4. It's 4 times worse. So this would have a drag of 160 here, not 80. It doesn't, double the speed. You'd think it would double the air resistance, but no, that's squared right there. This power function that we're talking about means that as I double my speed, now I have 4 times worse drag. So she's right. Slow down, save some gas, save some money. Up to you, whatever. Um, Here is kind of a little chart that shows how even powers and odd powers work. We've already talked about that. And it also shows what if you have a positive number out in front of it, a number that's greater than zero versus a number that's less than zero. We've kind of already said that, just flips it upside down. And there you see it again. A positive coefficient. This might be, something like f of x equals 3x squared or x to the fourth or x to the sixth, some kind of even power, right? And that's a positive 3 out front. It's bowl up. It's opening upwards like that. Both ends are approaching positive infinity. Meanwhile, if I had the same function but just put a negative number in there, negative 3x squared. All it does is invert it. It flips it upside down. That negative sign right there does that. The 3 kind of tells me how fast it goes up. The power makes it go up faster, all that. Over here, you've got your odd functions, and no big surprise, right? Either it comes up from the bottom through the origin and back up. Again, we're interested in the end behavior there. Or if you put a negative sign in front of it, then it's going to flip it and it's going to go like that. All right. Now, that was power functions, one term. Those are kind of straightforward, kind of easy to think about. When we think about polynomial functions, and again, we've already seen quadratics, which is a type of polynomial function. They get a little more involved because there's more going on. You're still going to have that leading coefficient. You can see that they talk about the leading term right here. That first term is, of course, the most important. Why? Well, because as I change x, I'm raising it to the fourth power, and that's eventually going to be much bigger, much more important than x cubed, x, or certainly 7, right? So that leading term kind of governs the big picture version of what's going on. These smaller terms, and I'll mark these 2 here, can put that wiggle in there like I was talking about. And of course, we know that a constant added or subtracted to the end is nothing but a vertical shift. So that's what's happening right there. And once you put these wiggle terms in there, highly technical term right there, um, that's going to determine what happens in the middle here. You can see the parabola coming down, right? X to the fourth is going to be an even power. So, and it's got a positive coefficient up front. We know it's going to be in behavior up, and that parabola is doing its thing right there. But those wiggle terms in the middle are making it do this. When X is small, close to 0, then you could see that and actually, we have a different problem up here. Well, I guess this should be, yeah, these are 2 different x to the fourth. Well, 2 different polynomials, both with a degree. degree is the highest power, so the fourth degree of 4 there. Um, but there's one way to write it out. Let's just skip over to this one and forget about that other one. Um, Here's that constant I was beginning to speak of there, minus 1092. And you can see that this thing, the whole thing has been shifted down. That would be our y-intercept. Why? Well, because at that point, x equals 0. And if I put x equals 0 in there, all of this stuff is going to go away, and I won't have anything except that downward shift, downward, the vertical shift of 192. When I start putting these numbers in, though, when I put 1 in all the way through, it's not going to be too much. This actually would be the biggest one, wouldn't it? 1 to the fourth, minus 14, 1 to the third, minus 31, 1 squared, plus 124 times 1. That's going to add 124 right there, which is going to bring this thing way up. The others may move it up or down a little bit, but that big coefficient is driving it more than x to the fourth is. But when I get out here to the 10, x equals 10, 10 to the fourth, that's 10,000, right? That's going to swamp this guy here. So that's what's making this go the way it is. Now, um, this is written two different ways, so I kind of wanted to say something about that. Eventually, we're going to learn to do this, but here is one way to write that function that you see right there. And of course, we would say that that's in descending order, where I've got x to the fourth, x to the third, all my x squareds together, x coming next, the constant. The descending order on this degree 4 polynomial function right there would look like that. However, there are ways to break that up, to factor it. We know how to factor quadratics, but eventually we need to know how to factor these guys too. I'm going to show you some tricks on that, I think, in the next section. This will break down, and you can express it like this. Okay? You could FOIL this back out, FOIL these two right here, FOIL these two, and then whatever you get, multiply those two together, and you'd end up with that mess at the top, right? But once you've got this thing factored and you have x minus 13, x minus 6, x minus 2, x plus 7, makes it really easy to find the roots. Why? Well, because the roots are where it crosses the x-axis. You can see there are 4 of them here. We would kind of expect 4 because the degree shows us the highest number possible of roots. So there could be up to 4, but I would never have 5 here. No 6s, 7. There's no, I can't go past 4. Now, they might not all be real numbers. We saw with the quadratics, and we see it again here. What if I shifted the whole thing up? I don't know, 2,000 spaces. It might do, well, let's let it come down and touch. There. All right. Might do this, right? If I shift the whole thing up a little bit, I might have 2, or it might come on up and just touch in that one spot, or not at all. All right. But so, there's a lot going on here, but 4 is the most I could ever have. And with this thing factored like it is, we know that all we have to do is set that whole thing equal to 0. And now I'm multiplying 4 things getting 0. So that means either x minus 13 equals 0, which would be x equals positive 13, just add 13 to both sides, or maybe x equals 6. I went ahead and set this equal to 0, move the 6, or x equals 2, and x equals negative 7. I have 4 roots, and you can see the mark there on the graph where I've got one at negative 7, one at positive 2. That's these guys. Here is the x equals 6, and the last one's out there at 13. So if you can find one of these polynomials, factor it, just like we did with quadratics. It's real easy to get the roots out of that and to build that polynomial. Or you can go either way. You have the polynomial, you can find the roots. If you have the roots, you could come in and say, well, I need one at negative 7. So that would be like x plus 7. I need one at 2. So x minus 2 would be an option. Need one at 6. Need one at which one did I leave out? 13 up here. So, really for that one, I'm just kind of going backwards on this and say, oh, if it's 13, then move it over. X minus 13 would be the last one. There's my polynomial, and I could multiply that out and turn it back into this form if you want to do that. All right. Again, we'll do more of that later, so don't worry too much about it now, but that's where we're headed. I got another little physics example for you. Again, you don't need to know physics here, but just thought you might find it interesting that we have a formula that gives us the position of a object and at any point in time. I guess this is already up here. Position at any time. Okay. You tell me what the T is. You start a stopwatch when the car starts, and I can tell you where it's going to be if I know the acceleration of the car and how fast the car was moving at the beginning. We call that the initial velocity. And if the car didn't start at the zero mark, I need to know about that. So this would be the initial position. Okay, but you can see that's a polynomial function, position. Um, and there's basically three things. Where did the car start? How fast was it going at the beginning? And did it speed up? And you take those three numbers, plug in a time here, here, and not there, and you'll know exactly where the car is uh, going to be at any point in time. As long as A, V naught, and X naught don't change, then you've got that figured out. So this is kind of a summary here. Whenever you come across a polynomial, and it would be true for a power function too, with only one term, but multiple terms, one term, whatever. We're always interested in the degree of that thing. What is the highest power of that polynomial function? Because that's going to determine the end behavior. Is it both up, both down? Is it one up, one down? What's going on with my big picture stuff right there. The roots kind of go remark on what's happening in the middle. So, if I see it do this right here, then I would be inclined to guess that since this has one, two, three roots, that I have a cubic function. It's certainly odd, right? It's certainly an odd function, an odd power. So my choice would be x cubed, x to the fifth, x to the seventh, dot, 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 and maybe it really comes up here and it has a whole bunch of wiggles back and forth and comes down through here. Maybe there's some more wiggles. That would indicate a higher degree right there, but it's at least three. So I would kind of start with that and see if I could make that work and whatever. I'd be interested in the y-intercept because that tells me where this thing is crossing the y-axis. It's right here. That's going to tell me something about that constant at the end. Um, Slope is a pretty important thing. We talk about that a lot in calculus, and of course you don't have to know calculus here, but just think about this green line that we've drawn. If this were a hill, you were driving your truck up this hill, it'd be pretty steep, right? And here it's not so steep, and here it actually levels out flat, and then you're going downhill again and downhill. That's the slope of that function at every point in time. And a lot of economics, if you play the stock market, it doesn't really matter what the value of that stock is today. The whole deal is it going up? Is it going down? What's the slope of that thing? And people like it when the slope is up if they own, because then they bought and now it's worth more so they could sell it and stuff. I'm not into money in stock markets and games. I don't have interest in that, but that's that. A turning point. Notice that, like right here, for example, we were going uphill and we turn and we go downhill. So, if you kind of zoom in, let's draw a little window right there and look at that. See how that's a maximum? And then if I did it down here, there would be a minimum right there. So we're interested in turning points that tell us where things stopped going up and started going down. And you could graph that in politics and economics and physics and all kind of good things. The last one I'll mention here is called an inflection point. An inflection point is a place where, um, see how, I'm gonna go to the highlighter here because we've kind of used everything up. See how for this region right here, it's kind of concave down, and for this region over here, it's bowl up. So I was bowl down, here I'm bowl up. Somewhere there in the middle, it had to flip. It had to change from being bowl up to bowl down. And that's called an inflection point where it changes direction. I don't know if you can see that yellow or not. But and of course we don't need to do anything with the inflection point, but you'll hear people use that term. Oh, today was an inflection point when, whatever happened. We seem to be inflecting a lot these days, and so who knows? Who knows? But that's the things that we want to know about these polynomial functions and what's going on with it. They'll tell us a whole lot about the behavior of whatever system this is set up to model. We'll talk more about finding the roots. We'll talk more about how to factor those polynomials and stuff. But it's pretty neat stuff. So thanks for stopping by. Have a good day. Let me know what I can do to help.